this point right here, how would you figure out which direction you're traveling in at that point? What would you figure out?
You can pick direction, point, and
Yeah, what's that called?
Gradient.
The gradient, right?
Right.
So if you wanted the gradient here, you could get this gradient, right? Let's say you were traveling along this level curve right here, this 10 right here. What direction would that gradient be going in?
Perpendicular.
To what?
To the that green line.
Okay, I'm confused here. You just answered that one correctly, so I'm trying to figure this out. So if I'm traveling along this right here, and I stop right here, and I look at what direction am I heading in? You agree you're heading like this, right?
Yeah.
Okay, good. What happens if I'm traveling along this level curve right here, and I stop right there? What direction am I going to be traveling in?
Exact opposite.
Exact opposite. What can you say about those two vectors? And it depends on which direction you're going in terms of, like, I could be traveling in this direction on the level curve or this direction. What can you say about those two vectors? They are what?
Opposite.
No, I'm saying
Oh, they're
irregardless. No, not proportional, and it doesn't matter if they're opposite. Yes, those specific ones are opposite, but what I'm saying is, what happens if I'd asked you if you're traveling in this direction on the level curve?
Same magnitude.
Nope, not the same magnitude. They definitely not have to have the same magnitude. For example, if I'm looking at this right here as opposed to this right here, and I look at the lines of tangency here, are they going to have the same magnitude? No, they're not. What are they always going to be, though? Regardless if I'm traveling this direction or this direction, yes. They are always going to be parallel. They're always going to be parallel to one another. Do you understand that, everybody? So when you're trying to maximize a surface and you have a constraint or a path, so one way to think about the constraint, you're looking for what level curve is the path tangent to. So you're looking for the place where the gradient of the constraint is proportional to the gradient of the surface. You'll see this. You'll see something that looks like this. You might have seen this lambda thing. What kind of value is lambda? It's a Lagrange multiplier, that's correct. But in specific, what kind of value is it? That's not a distance. What kind is it? It's a constant. Thank you. It's a constant. Two vectors are parallel if they are scalar multiples of one, proportional scalar multiples of one another. So the point is, if you find a point, and if a point is the maximum value, the gradient of the restriction is going to be proportional to the gradient of the surface. Does that kind of yes, it's important. Kind of make sense right now? Kinda. Now here's the thing. What makes using this fact hard has very little to do with calculus and way more to do with logic and algebra. They actually state it out loud in the calculus textbook. They give you in several sections in this. This is 14.10, I think. I think it's 14.8?
Yeah.
14. Thank you. It's 14.8. In 14.8, and for some reason this is just freaking out here. In 14.8, it actually says, let me pause this here, is something like, there is no one way to solve simultaneous equations. And you already know that. You can do some things with substitution, you can do elimination, but many times it's just going to take a lot of creativity, and the book actually says that. I kind of like it when books own up to that fact, that there isn't just like one way to do something, you have to be creative about it. What this means is we have a shorter way, theoretically, of solving for minimum and maximum values across these bumpy surfaces. Before, when we were looking for we'd find the critical points, we'd do like v sub x, v sub y, and then we'd get some nasty set of simultaneous equations. This allows us to kind of simplify that process, but the algebra can be nasty. Just please know that the algebra can be nasty, and sometimes it takes a really clever observation. It's kind of like the squeeze theorem. The squeeze theorem itself is not too difficult to understand, but finding the right inequality to start with can sometimes be really hard. Just because the answer is really elegant, actually sometimes especially because the answer is elegant, probably means that it's hard to see. Let's actually try one of these. Which one's the bumpy surface?
That's the x, y,
Not circle.
Yeah, not the circle. Yes, that's the bumpy surface. So if you input any coordinate x, y, it'll pump out x squared plus 2y squared. And what's your path?
X squared plus y squared equals 1.
X squared plus y squared is equal to 1. So potential maximum values are going to occur where the gradient of the restriction is proportional to the gradient of the bumpy surface. So how do we go about finding the gradient of each? Well, you really like finding gradients, don't you?
Yes.
What's fx xy?
Uh,
2x. What's fy xy?
4y.
4y. So the gradient of f of xy is equal to what? 2x what? You can do it this way, sure, plus what? 4y, isn't it j? Yeah, you don't want k yet. Okay, so then let's look at, this is our restriction, right? That's our restriction. So when you're specifically finding the gradient of that, what's our gradient of g going to be in terms of x first? 2x, yep. And what about our gradient y? What's it going to be? 2y. So therefore, our gradient vector, not f, g, is going to be, it's going to be what?
2x
Plus
2y
2yj. Okay, so let's go back and take a look at what we...
Anything between 0 and 1.
X?
Yeah.
If we just had this, and I just said they had to be proportional, yes, y could be 0 and x could be anything. Anything, but look, it's x squared plus y squared equals 1. Equals 1. So if we know y is 0, what does x have to be? If x squared plus y squared is 1 and y is 0, what does x have to be?
Oh,
1 or 0. 1 or negative 1. Sorry, 1 or negative 1. So if I ask you what is the maximum value, plug things in here, and what do we think the maximum value is going to be? We have f of 1, 0, which is going to be actually equal to f of negative 1, 0. And what's that? What should that equal?
1.
1. That's along that path. Now let's see if we can visually verify this. It gets harder to visually verify things in this class because a lot of the surfaces are terrible.
So,
Keep in mind, this is, listen. This is the maximum along that restriction. Could this surface get a lot bigger than 1?
Yes.
Yup.
Absolutely. Absolutely. But along that path is what we're talking about here. Along that path. Yes.
Is this used for like?
Okay. So someone else who wants to do the gradient of G. Anybody? No one? Okay, I'll pause it again because you're not being lively. It's fine.
Please.
Yeah. So, okay.
Record now.
So what do we now know? We know that 2x has to equal lambda times 2x minus 6. We know that 2y has to equal lambda times 2y minus 2. And we know that 2z has to be lambda times what?
Z minus 2 plus 2.
2z plus 2.
And all the lambdas have to be the same.
Yes, at the same time. That is correct. That is
Let's
correct.
factor out a divide
Hold on. Yeah, x isn't 3y. That's good. And what y is y. Great. And what is z? Z is negative y. So what do we end up with? 9y squared plus y squared plus y squared is equal to 4.
Oh.
4. So y is equal to plus or minus 2 over root 11. So what does that mean z is equal to?
Negative.
Wait, so be plus or minus.
It's minus or plus.
Plus or minus, yeah, exactly. That comes up every once in a while, and I love that. What's the opposite of plus or minus?
Plus or
Minus and plus.
Minus and plus. I guess that verbally communicates that there's some thought process in there. So how do we get x? What's x equal?
3y.
Plus or minus 6 over root 11. So I have a question for you. How many points did we just identify?
6,
9.
8.
8 points.
Yeah.
We just isolated. We just solved. We got 8 points. How? Plus or minus y, plus or minus z, plus or minus x. So each of the entries can be 2 different things, right?
Wait, don't they have to pair up though? Like the positive y has to pair up with the negative.
Do they?
No, it's all squared.
No, because our constraint, let's look at our constraint for a second. Our constraint is x squared plus y squared plus z squared, right? So do they? That's a really good observation, though. You're absolutely true. You're absolutely right. And that sometimes you have to be very, very careful about that. So the opposite of z. So let's build our points so far. So we know that y can be 2 over the square root of 11. If that's true, what does z have to be?
Negative of that.
Negative of that. Negative 2 over the square root of 11. And there's still an x value right there. Or if this is negative, this has to be positive, because it tells us y and z have to be opposite, right? And what do we know? If y, what's the relationship between x is always 3 times y? X is always 3 times y. So we were just a little sloppy at the end. I'm sorry about that. So this is 6 over root 11. And what's the other one?
Negative 6 over root 11.
Negative 6 over root 11. So then the question is, Gately, how do we figure out which one is the min and which one is the max?
You plug them in to the distance equation.
Yes.
What's your name, Gately? Is that your?
That's my last name.
It's your last name, right?
Yeah.
I've been calling you the right name, right? It's always kind of a phobia of mine.
You called me
Gatley?
Yeah.
Yeah.
And Jefferson too.
Jefferson? Well, Jefferson's pretty good. That's your full name, right? Yeah, so I was kind of definitely right and wrong at the same time. Okay.
Wait, if Jefferson's real name, how are you wrong?
Because he doesn't go by that in common parlance. He likes to be called Jeff.
Oh, yeah, I know that.
So therefore it's like people calling me Joshua. Technically that's my name, but for 2 different reasons you guys shouldn't be calling me that. Why?
Because you're
So
my
right now,
teacher.
then you're-
I'm your teacher, so I go by Mr. and also I
Mr.
generally go by
Schwab.
Josh. Joshua is like the last out of like 5 different names usually that I
What
go
else do you
by.
like to be called besides Josh and Mr. Seaman?
To adults, turn 18 and graduate, and then I'll tell you.
I'm 18. Oh, I'm
I know, there's 2 qualifiers there. Okay, so we have 2 points. So what was our distance formula? Where's our distance formula? Let's go back up here. This one, right?
When you get the chance, will you use your document camera and take a picture of Jen's
I'll
thoughts?
clip it into our
Yep.
class note.
I will absolutely clip that in. You really did that?
Yeah.
Whoa, dude. I'm very rarely impressed by students.
And you said it only took him 3 hours.
Yeah, well, the first one took me 3 hours too, and I knew what I was doing, so good job. Okay, so in this one here, how do you figure out, just by looking at this, which one's going to be bigger than the other?
Duh.
Is there any way to concretely do that?
You just plug them in with a
The
calculator.
last one is the maximum.
This compared to that, that's the max, isn't it? Yeah. Now, we haven't figured out what the max and min values are, but we're just saying the max is here, right? And that the min is
There.
here.
There.
Max is here, max is here. Okay. We okay?
It's
No,
neither
it's
here
there.
nor there.
I think you're okay.